Good morning, student. Today in this session we are going to see image compression, that is our chapter number 6 from digital image processing. So in very first, image compression. Image compression is the process of reducing the amount of data needed to represent a digital image. Okay, so whenever we are going to represent any information, in that information and data, these are the two things are there. So all data is not but the information and data is different, two different things. So to represent that information we will require the data, or to convey the information we will require the data. So this is done by removing the redundant data. So objective of our image compression is to decrease the number of bits required to store and transmit without any measurable loss of transformation. So there are two types of digital image compression: lossless or error or free compression, or second, lossy compression. So what is the need of data compression? If data can be effectively compressed, so we can significantly improve in data throughput. Second need, that whenever compression is done, it can reduce the file size up to 60 to 70%. Hence, so many files we can combine and make the compressed document. Then third, whenever there is a reduce the consumption excessive resources, such that hard disk space as well as the transmission bandwidth. Then fourth, compression can fit more data in small memory, and thus it reduces the memory space required as well as the cost of managing data. So these are the needs of data compression. So in data compression or image compression, what is mean by redundancy or data redundancy? Let us see. So in data redundancy, relative data redundancy, so here we are going to take or consider two data sets, that is N1 and N2. So in that information carrying units are there. So same information, okay, so in data sets. So how we can represent that the same information, that is depending upon that the compression. So the data redundancy is used to compress the data. The relative data redundancy is given by R of D is equal to 1 minus 1 upon CR. So what is CR? That is compression ratio. So compression ratio is given by the same data or same information which is in a N1 by N2. So based upon these two values, there are three different cases so which are listed below. Suppose if N2 is equal to N1, means same information represented in a different data sets, that is N1 and N2. So no redundant data is present in first set. If N2 is very less than N1, highly redundant data is present in a first set. And third, if N2 is very greater than N1, highly redundant data is present in second set. So depending upon this, we can reduce the data which is required to represent the information. So there are types of redundancies. So very first type, coding redundancy. So in this coding redundancy, a code is system of symbols used for representing the information. So a code word is a sequence of symbol representing the information. So code length is defined as the number of symbols in each code word. So a resulting image is said to have coding redundancy. So if suppose it is gray levels are coded using more code symbols than actually needed to represent the each gray level. Then means coding redundancy is nothing but we are going to use the code word which is represent the symbol. So whatever the original representation of that data, according to that coding redundancy will require the less number of bits to represent the same data. So what is the average length of code words. A gray level histogram of an image is used to construct codes to reduce data redundancy. So multiplying the number of bits used to represent each gray level with the probability of occurrence of that gray level and adding all such products gives the average length of the code word assigned to different gray levels. The average number of bits needed to represent each pixel is given below. So L is nothing but that the number of gray levels. So L average is equal to summation k from 0 to L minus 1 L of Rk probability PR R of k. So where L of Rk is number of bits used to represent each gray level. PR of Rk probability of occurrence of gray level Rk. So probability of occurrence is given by n of k divided by n. K varies from 0 to L minus 1. So where capital L is number of gray levels and nk number of times the kth gray level appear in image. And small n is total number of pixels. So total number of bits is given by the total number of bits required to code an m by n size image is given by, so L is the length of that the m by n image is equal to m into n into L average. So to avoid redundancy, coding redundancy can be avoided and thus data compression can be achieved by assigning fewer bits to more probably gray levels and more bits to less probable gray levels. Okay, so this is the coding redundancy. Next is the interpixel redundancy. It caused by the interpixel correlations within an image. So interpixel correlations are the structural and geometric relationships between objects in image. So in this autocorrelation is used. So autocorrelation coefficient is given by, so it is the computed using gamma of delta n is equal to that is scaling factor a of delta n divided by a of initial value, that is a of 0. So where a of delta n is nothing but the scaling factor given by, so scaling factor is 1 upon capital N minus delta n summation from y0 to n minus 1 minus delta n f of xy into f of x y plus delta n, where n is again number of pixels. So in this, to avoid redundancy, interpixel redundancies is an image can be reduced by transforming the 2D pixel array into a more coefficient format. So transformation used for this purpose is known as a mapping. Okay, if the original image elements can be reconstructed from the transformed data set, the mapping are called a reversible mapping. So this is interpixel redundancy. Next is the physiovisual redundancy. So every time human eye cannot see all the information. Okay, so it is sensitive for the some part of that the information. So the human eye doesn't respond to all information with equal sensitivity. So some information may be given less importance when comparing to the other information in normal visual processing. Such information is said to be physiovisual redundant. So these are the redundancy techniques which we have seen. Then next is nothing but the fidelity criteria. So fidelity criteria is used to evaluate the information loss during data compression. So what is the need? There is a loss of real or quantitative visual information when redundancy is removed. So means what? When we are going to apply the redundancy for image, so at the time of that the receiver side, when we are recovering the data, there may be a loss. So thus there is a chance for losing the information of interest. So therefore there is a need to quantify the nature and extent of the information loss using repeatable and reproducible criteria. So according to that, there are two types of the fidelity criteria: objective fidelity criteria and subjective fidelity criteria. Objective fidelity criteria. So in this objective fidelity criteria, It is expressed at the level of information loss as a function of two parameters. So first is the original or input image, and second is the compressed and successive decompressed output image. So here root mean square error we are going to calculate. So root mean square error means between the input and output image. So if it is very good example, it is very good example of objective fidelity criteria. So how we can take the error between the two image, that is represented in the first equation. E of xy is equal to, that is output image f dash xy minus input image f of xy. So total error between two m by n size images is given by E total summation x varies from 0 to m minus 1 and y varies from 0 to n minus 1. So output image f dash xy minus f of xy. The root mean square error E RMS between f of xy and f of xy is obtained by E RMS, that is square under the square root 1 upon mn summation from x0 m minus 1 to the y0 to n minus 1 f cap of xy minus f of xy square bracket square. So it gives you the advantage that simple and convenient technique to evaluate the information loss. Next is the subjective fidelity criteria. Since human prescription is based on subjective quality, means from all information human eye only gives the importance to some part of that information. So it is more suitable to use subjective fidelity criteria to evaluate the information loss. So in this concept, this method is implemented by showing typical decompressed image to a number of viewers. Then their evaluation is averaged to take a decision. So this evaluation may be done using a rating scale or side by side comparison such excellent, better, same or worst case. So next point, that is image compression model. So the figure shows that general image compression system. So in this encoder and decoder shows. So image compression systems composed with the two distinct functional components, that is encoder and decoder. So encoder performs the compression and decoder, which is decompression. So let us see the one by one that the part encoder and decoder. So in the figure, input image is applied for the mapper, then mapper output given to for the quantizer. So quantized means in mapper will reduce some of the redundancy, then quantizer means quantizer level will define, and symbol coder gives that the code word length for that data, so that whatever the input image f of xy is compressed at the end of the symbol coder, and at the receiver side a symbol decoder is used to recover the data and inverse mapper is used. So at the end of that the image compression system, the original image or the output image f dash of xy is obtained. So here source encoder and decoder we are going to see in detail. So in encoder size, or we can say compression process, a mapper. So mapper transforms f of xy into individual format designed to reduce spatial and temporal redundancy. So this operation generally is reversible and may or may not reduce directly the amount of the data required to represent the image. So run length coding is example of a mapping that normally yields compression in the first step of the encoding process. So the mapping of an image into a set of less correlated